Okay, let's start for the second part. So for the second part, I'm going to talk about the speaker detection. Actually, speaker detection is we can see it as a type of source separation. So it only focuses on the detection of the target speakers. So the motivation of speaker detection is to mimic a human's top-down selective auditor attention. So giving the a reference clue of the target speech, then we can use the network to learn the to estimate the speech of the target speak. So it's just like our Gold party effect and to overlook other interference speaks voice by focus our attention on the interest. So this is speaker detection actually address the unknown number of speakers in the mixture. So also solve the global speaker permutation ambiguity problem because it only focuses on the target speak. So without many outputs. So it's only have one output. There is no permutation problems. So first, we also first consider the frequency domain method. Actually, in the speaker detection, according to the different of reference clues, we divide them into the audio assisted, visual assisted, and the heterogeneous speaker detection. So for the audio assisted one, we first introduce the frequency domain method, which is also we use the short-Fourier transform to decompose the signal into a magnitude and a phase spectrum. For the reference speech, actually we can record a speech as a in row. So we get the speaker unbindings, which is to categorize the target speak. So with the magnitude of the mixture together with the speaker and unbindings of the target speak, then we use the speaker ejector to estimate a mask. This mask is only for the target speak, so we can get the estimate the spectrogram of the target speak. Then we use the phase of the mixture speech. Then we reconstruct the symbols. So the one for the frequency domain audio assisted speaker detection is the speak beam based, also the voice filter live, and our work on the based on the speak beam. So here in the speak beam method, they try to use several layers of feed forward to estimate the weight. This weight is used to get the importance of each subnetworks. So after that, they sum them together. Then use this information to estimate the mask of the target speaker. So after that, we try to improve the framework of the speak beam by several points. The first one is we use bidirectional LSTM to learn the speaker bindings. Another one is how we combine the speaker and binding information into the ejector of the target speaker. So here we use the bidirectional LSTMs to estimate masks of the target speak. Another difference is in the loss function, we try to use the context information, which is verified effective in the speech separation. So we also use the here to consider the context in the loss functions. As we know, in the speaker detection in the frequency domain method, we are also using the phase of the mixture. So this kind of phase is not optimal. So we also try to propose the time domain one, which is I use a similar speech encoder and decoder to replace the short-time Fourier transform and the invert short-time Fourier transform. So similarly, we have the speaker encoder to encode the reference speak into a speaker unbinding to characterize the target speak. After that, we use the speak unbinding and the unbounded coefficient to get the mask of the target speak. Then we use the speech decoder to reconstruct the signals. Here is another work we try to use because here for the speech encoder we can use several parallel one, each one with different the lengths. Then we can have the different temporal resolutions. So combine with them, then we can do the separation. With this loss, with this parallel one, we can improve the performance. Also, we combine the speaker ID loss to further improve the performance. Because sometimes if we only this part we only need to characterize the speakers. Then if we add a speaker ID loss, then we can better learn the speaker unbinding features. Another one is we try to use the shared speech encoder. Because in the previous work we still use the frequency domain, for example, the field band as features. So to improve, make the mixture speech and the reference speech into the same vector space, so we try to use a shared speech encoder, which is to transform them into the same feature space. Then with this performance, with this shared one, we can further improve the performance. Another one is we try to study how can we reinforce the attention, because previously we say we have the XT, right? This XT is a pre-recorded signals. Along with the time, the speaker may have the characteristics of the speaker may have a slightly change. For example, we call it seek. Then the characters with the normal one is different, so we can use this kind of adaptive speaker unbindings to reinforce the attention, which is we can do the multi-run. First, we have the traditional one. We have the pre-enrolled speech as a reference to get the speaker unbinding to estimate the speech of the target speaker. Then we use this as additional information to the speech encoder to get the better speaker unbinding. Also, we can use in the speech separation part, which is similar to the multi-iteration speech separation systems. So here we can the combine of this speaker information is in two different cases. The first one is in utterance level, which means we combine with the original pre-enrolled, then we get the utterance level. Here we get the frame level because this ST is aligned with this YT. They are corresponding to each other, so we can have the frame level speaker unbinding information. So later we will study the performance of these different the combination of the speaker unbindings. So here we can see if we use the single iteration performance like this, the target is the pre-enrolled. If we do a multi-run, then we can improve the performance. Then if we only use the frame level, which is we only use here, don't combine the here. So we also can improve the performance. But if we combine the utterance and frame level together, we achieve the best performance. So we also evaluate how is the performance if we give less duration of speech, enrolled speech. So here is if we have the long reference.
In addition, US West Data Solutions Business Applied Communication.
So here is the enroll of the speak. Here is the mixture speech.
The best strategy,
I'm sure of
he
it,
said,
period.
Yes, actually, we want to eject the male speech. Here is the ejected speech.
The best strategy, comma, he said, comma, is
If we use a short reference, just 2 seconds,
in addition, US West
then we can also improve the target.
the best
target speaker
strategy,
voice.
comma, he said, comma, is
So here is a comparison with the three separation systems on the voice to mixture database. So the red block actually is a speaker ejection system. So this is a frequency domain. These three are the time domain. Actually, these three is based using the temporal convolution networks, which is similar to this one. If we can using the improved network structures, I think we can further improve the performance of the speaker ejections. So here we also evaluate the performance on different scenarios. For example, in the noise case.
As part of the marketing plan, the company will begin airing television commercials during prime time.
This is estimated.
As part of the marketing plan, the company will begin airing television commercials during prime time.
So this case is to remove both the interference speaker and the noise. So this is a vibration case.
As part of the marketing plan, the company will begin airing television commercials during prime time.
Here is the estimate one.
As part of the marketing plan, the company will begin airing television commercials during prime time.
So here we are doing the devibration and the removing of interference speakers together. This case is we have the interference noise vibration.
As part of the marketing plan, the company will begin airing television commercials during prime time.
Here is that result.
As part of the marketing plan, the company will begin airing television commercials during prime time.
Okay. So for previous case, we only consider the speaker is present. For example, this case, we have the target speaker A, which is present. Either has the interference speaker or non interference. So we have another case which is most of the time the target speaker may not talking, so we only have the voice of the interference. So how can we have a universal system to handle all of this case? Actually, we propose to use to design a loss function to handle this for case. Another one is sometimes because parental audio assisted speaker ejection, we need to have the voice of the target speaker as a reference. Sometimes we don't have this kind of information. How can we do speaker ejection? Actually, we also can use a visual. For example, when we buy a ticket using audio-visual assisted ticket machine, then we can use visual as information. Then because this system cannot ask the passengers to record a speech as in row, so we can use the camera to capture the lip readings of the speak. Then we can use this visual encode to get the information of the target speak. Then we do the ejection of this target speech. So after that, we further improve the performance by learn speech and lip synchronized network, which is we try to use self-supervised learning to learn this kind of information. Because as we know, when we are talking, we talk in different phones. Our lips are different, so we can have the synchronized signals. Also, we simulate non-synchronized signals, which is we randomly shift the video and the audio to get this non-synchronized system. So with this system, we can try to learn synchronized features, which is captures visual information. With the kind of information, we can do the speaker extraction. So based on this work, we can see actually the proposed visual assistant system, also the synchronized visual systems achieves better performance than the previous speech separation systems for both 2-mixture and 3-mixtures. So we also evaluate our performance on different data set, which means we train on Vox Cerebral 2, then we test on real domain, which is LRS2 and LRS3. We also test on studio case. You can see our system actually robust to the unseen data set. So here is a demo between the debate of Trump and Patton.
I've already fixed it.
He has never offered a plan.
Fixed it to an extent.
He has never done a single thing. How to do that? He has never offered a plan. He has never
So here
done
we
a
focus
single
on
thing.
the
I've already
Trump's
fixed it.
voice, then we
I've
only
already
have the
fixed it to an
Trump's
extent.
voice.
Obamacare, as you might.
So another case is when the visual is missing, how can we do the visual assisted speaker extraction? For example, sometimes the camera cannot capture the deep information. So actually, this work is proposed to do the visual information reconstruction. Actually, to do the unbending impacting. To recover the informations missed. So another work we talk about the audio assisted, visual assisted. Also, can we have some concept-based one? For example, we only have proposed some words. For example, these can words. Can we extract the speech of these two words? Then this work actually studied the environment sound extraction using automatic words by using the words as reference information to do the sound extractions. Here, this is similar. Actually, we have other different concepts. We can say. We want to have the female speech, then we give the female labels, then the output is female. We have the speech of the male, then we give the male labels, we can have the speech of this male. So also we can say the speech far from the mic, the language of the speaker is talking, also the loudness. Then we can give this kind of information, we can do different kind of voice ejections. Also, for the visual one, if we totally don't have the visual information, for example, we have a mask taken to, we cannot, the camera cannot have the lip information. The unbending impacting works also fails. So how can we do that? Actually, this work study interest information is gesture. Actually, our gesture sometimes is corresponding to what we are talking about. So they design of different gestures using these gestures to do the speech extraction. Here is the demo.
Is they make a cell phone, go down to the stall, they sell some, they look at the other kids' stuff, go up, make a couple thousand more, go down.
Peoples, and
doesn't this sound like a software thing? It sounds like agile software.
The struggle to keep African narrative alive has been one of the most consistent and hard-fought endeavors of African peoples, and continues to be so. The struggles endured.
So actually from this demo, we can see that gesture information also can be used to do the ejection. Actually, it helps. Actually, previously we mainly talked on the single channel case. In this talk, actually, I don't want to include too much works on the multi-channel. Here I just give an example. If we do the single channel well, then we also can extend the work to the multi-channel, which is we do the speaker rejection with our previous single channel systems by adding the additional information of the special information, which is the direction of the target speaker. So we can do the network-based beamforming to reconstruct the symbol. Also for the multi-channel one, actually there are many works on this to do the using the network to do the mass estimation, then use the NVIDIA to do the beamforming. Also, they designed the GSM or the network-based beamforming. So if you are interested, then you can look at these papers. Before I say we talk a lot of works on speech separation and speaker ejections. So why do we do this kind of works? So now I would like to introduce some downstream tasks. We want to use the appropriate separation or ejection system to improve the downstream task. For example, the multi-talk speaker verification and the multi-talk speech recognition. So why do we want to have this speech separation or speaker ejection system to speaker verification? Because sometimes we have the scenario some of speakers are talking together. So for the speaker verification systems, if they all talking together, then we give this feed to the speaker verification to identify whether the speaker is the enrolled speaker. So it's impossible because the speaker verification system will have the unbending or the characteristics of this mixed speakers. Then it's not easy to verify and compare with the enrolled speaker. So what we are going to do is to do the direction first. This is a try to do direction, but direction it means we try to segment the speech without overlap, but they are assumed in the same sequence. So we can do the direction to identify which segment is belonging to which speaker. But if the speech is overlapped, for example, they are overlapped in the spectral domain. So how can we do this? One is we can do the separation, then identify the outputs with the enrolled speaker one by one. Another work is we can do the ejection because our audio assisted speaker ejection requires an enrolled speech. The speaker verification is providing the enrolled speech, so we can do the speaker ejection perfectly. So what we can do is we can use the enrolled speech of the target speech, do the ejection first. We get this speech, then we use this eject the speech compared with the enrolled speech again to do the identification or verification task. So actually in this system, we compared several different speaker ejection systems to compare the performance based on these two frequency domain and the time domain systems. After that, we also propose to use end-to-end system, which is we would like to train the speaker ejection and the speaker verification together. So here is the database we are going to evaluate on. So in the database, they have different percentage of overlappings. So the baseline is the original system, SV systems. Actually, we train using the clean data. We evaluate on the mixture. We don't use the speaker ejection as a pre-processing. So the accurate is very high. If we are using the speaker ejection system as a pre-processing, then we evaluate the performance. Actually, if our training doesn't see the ejection system, it can achieve improvement. If we add the ejected speech into the training, then the performance can be further improved. If we use better speaker ejection system, actually the performance can be further improved. So this outbound means we are training and test on both on clean data, which is only one speaker is appeared in the input. So the performance of accuracy is 3%. Here is if we use the joint end-to-end training, which is we jointly train the speaker tracing and the speaker verification system, then we can further improve the performance. Okay, for the multi-talk speech recognition, actually, we have a lot of systems. Most of the systems are doing the overlap the speech recognition end-to-end. Actually, we have the end-to-end speech recognition systems. They combine the speech separation and the speech recognition together to do the multi-talk speech recognition. So I don't list too much of the work. Here I just show some of works using the speaker ejection as a front end to do the multi-talk speech recognition. So this voice field live. Actually, I learned the speaker informations using a devector. After they train the devector, they do the speaker ejection. Then after they get the ejected speech, they use this speech to do the traditional speech recognition, where the speech recognition system is trained on single speaker. So in this work, they also proposed a loss function to solve the over-separation problem, because in our speech separation or speaker ejection system, sometimes we delete or over-separate the sound frames of the target speaker's voice. So this work tried to try to design a loss function to penalize these errors, which is the separations. With this penalize then the speech recognition performance can be further improved. Actually, in the real-world application systems, this over-separating system is very serious. So we need to release the, for example, we can have the interference voice remaining in our output, but we cannot delete. So this is a case we are going to use as a constraint to our system. So another work is our work using to do the full band speech enhancement or speaker ejection with wideband ASR system compatibility. What does it mean is actually we have a wideband system for speech enhancement or personalized speech enhancement. Personalized speech enhancement is also similar to our target speaker ejection, which is we only output the speech of the target speaker. So we also call it as the personalized speech enhancement. So we have this kind of for example, our online applications already have this kind of wideband speech enhancement system and wideband speech recognition systems. So how can we keep this kind of systems and to generate a good quality of full band signals? What we are going to do is we use the actually we divide the full band speech into the high band part and the lower band part. Actually, we for the noisy remove, we still use our existing wideband system. Then we use this output together with the high band part to do the high band speech enhancement. Then we have the high band the enhanced speech. Then we combine them together. Finally, we do some post-processing to reconstruct the signals. So here we have several switches to control our systems. For example, if we want to have the personalized case, then we give the reference of the target speak. Then we open this personalized switch. Then, if we want to output our SR system output, then we send the wideband part directly to our existing wideband speech recognition systems. So this one can be used to have some advantage, which is we can use our already existed wideband speech enhancement system and the wideband speech recognition systems. So another work try to do is how about we using the visual assisted speech rejection system to do the SR. It means we use the visual assisted speech rejection to eject the speech of the target speak. Then we send it to the our SR system. So this will conduct some experiment on the SR case. Okay. Next, I would like to talk about the challenges still remaining in the co-party environment for the speech separation and the speech rejection systems. For example, as we previously say, we designed a universal system to handle different cases. But this case is still very simple, just divided into 4 cases. Actually, there are some more. Then how can we improve the performance to handle all of these 4 cases? Because sometimes if we improve this case, then the performance in this case may be dropped. So how can we balance both of them? Also, if we add this case into our training, we find there will be some more over separation case. So how can we handle the over separation? Because the over separation is not tolerated in our real-time communication system. Another one is how can we have universal sound rejection systems? For example, we have different sound, speech, music, bird singing, or the sound noise. So how can we combine all of these cases and using a single system to handle all of these cases to eject the speech of what we are interested in? So another one is in some cases we want to control the speech, the energy of the speech, the source. For example, we have the background music. We have talk, right? For them on the online video streaming. So we have this. We already play some background music when the anchor are talking. So actually, sometimes we want to suppress the energy of the music, but we still want to keep the So one solution is we can separate the front end speech and the background music into different channels. Then we set a threshold to tune the energy of the background music, then combine them together. So this is some just some applications for the universal sound extraction or separation systems. Another is robustness. Actually, Professor will also talk about the two kinds of robustness. One is robustness to the environment. Another one is robustness to the languages. So, Professor, we have the unsupervised pre-training and mid-training. Also, we have the pre-training from speech enhancement system. We have the mixture IT system. But this kind of case still have some problems. Another one is for the language generalization. Actually, we use a simple solution, which is we combine different languages to train a single system. Then we use this system to do different kind of language processing. But sometimes we need to know how can we how many languages as we need to have this kind of universal system. So we still need to study. Another one is I think is a real-time implementation. Actually, in today's talk, I mainly talk about the offline systems. Actually, some of them are not extended to do the real-time processing because the network structure limits them to do that. For example, the dual pass or the iteration ones, it's very time-consuming. Another one is actually in the device, on-device applications, our requirement is quite strict. For example, in this iPhone applications, we need to have very small number of parameters of the network. Also, the computing cost should be very lower. Also, for the hearing aids, we actually the requirement is even strict because this device has lower power, so the computation should be very small. So how can we because if we design a real-time implementation by using small networks, then the performance of this network may be not as good as the larger one. So how can we transfer the capability of the larger model to the small model? So this is actually they have the teacher-student model transfer learning, but the performance may be not so good. So I think we still need to have some studies to do the real-time implementation. So okay, here are some of my supervisors and collaborators for all the works. So that's all of my today's talk. So do you have any questions? Okay, if not, maybe I stop here. Thank you for your attention.